Welcome to AI Paper Slop. Today we are looking at a massive new paper titled Ring Zero, Scaling Zero RL to a Trillion Parameters for Emergent Reasoning.
Yeah, and this is a really heavyweight collaboration from researchers at Renmin University, Ant Group, Tsinghua, and Zhejiang University.
Exactly. And we're going to jump right into the 60-second summary for you. So this team proved that you can take a 1 trillion parameter model, the Ling 2.51T base model, and train it to develop elite chain of thought reasoning.
And do it entirely from scratch.
Right, from scratch, zero human-annotated data, just pure reinforcement learning with verifiable rewards.
Which really strictly validates the bitter lesson of AI, that massive computation and scale just beat human-engineered heuristics every time.
They really do. The model spontaneously taught itself to use structured formatting, self-verification, even like parallel reasoning.
But, to make this work at the 1T scale without catastrophic collapse or just massive token bloat, the team had to design a highly minimalist 4-stage training pipeline.
Which was backed by some incredibly clever infrastructure tweaks to bridge the mathematical gap between training and inference engines.
Right.
So if you're an ML practitioner listening right now, you know how notoriously unstable RL is at scale. We are going to break down exactly how this team pulled off this trillion parameter balancing act.
It's a crazy balancing act.
Let's start with the core problem, right? We have a massive base model.
Yeah.
We want it to reason. Why can't we just, plug a standard off-the-shelf RL algorithm into this cluster and just let it rip?
Well, because standard algorithms run into two massive roadblocks when you push them to this scale. The authors brilliantly isolate them, and the first is this behavioral flaw they call length inertia.
Length inertia. Okay, break that down.
So to understand this, we have to look at how algorithms actually assign credit to the model. Standard approaches in this space like GRPO or group relative policy optimization, they rely on a token-level loss.
Meaning the algorithm evaluates and grades the model based on every single word or token it generates, rather than just looking at the final answer.
That is the mechanism, yeah. And honestly, early in the training process, you actually need that.
Right, because it doesn't know how to reason yet.
Exactly. You want to heavily incentivize the model to stretch its legs, to attempt step-by-step reasoning rather than just blurting out an immediate, unverified guess.
Makes sense.
But as training progresses, the model discovers a mathematical exploit. Because the gradient magnitude, the size of the reward signal it receives, scales directly with the length of the sequence, the algorithm is implicitly assigning higher credit to longer sequences.
Which brings up this lazy high school student analogy I was thinking about. Imagine a student who knows the exact answer to a test question in a single sentence, but they decide to pad it out into a rambling 5-page essay.
Just to guarantee a good grade from a rigid teacher.
Yeah.
Yeah, that's exactly it. If the model knows it gets paid by the word, it's just going to write as many words as possible.
Completely abandons efficiency.
Totally. The model learns that simply generating more tokens is a mathematically safer way to farm cumulative rewards, even for a trivial math problem that it could answer correctly on the very first try.
The sequence length just continuously extends over time.
Yeah, it ignores the actual cognitive requirements of the task in favor of just filling up the context window.
It is optimizing for the rubric, not the truth. I love that concept because it's so recognizable. But that is only the behavioral problem, right? You mentioned a second roadblock.
Yeah, the second issue is structural, and it is arguably much more dangerous. It is the system-level vulnerability they call the engine mismatch.
The engine mismatch. This is where the actual infrastructure starts fighting against the math, right?
Yeah, exactly.
So break down what is happening under the hood during this off-policy RL setup.
Okay, so in a typical off-policy setup, you are running two separate software engines. You have an inference engine. The authors used SGLang, which is responsible for generating the rollouts.
So that actually generates the text of the model's attempts to answer the prompt.
Right. And then you have a training engine, in this case Megatron, which looks at those rollouts, computes the gradients, and updates the model's weights.
And because these are two completely different software stacks, built for completely different purposes, they don't process the math identically.
They do not. Even when both engines are using the exact same frozen model weights, there are minute differences in how their internal kernels are implemented.
Like how they handle floating point arithmetic.
Yes. These micro-discrepancies mean that for any given input, SGLang and Megatron will produce slightly divergent logits.
Logits being the raw, unnormalized scores for how likely the next token is.
Exactly.
Now, in standard pre-training, a fraction of a decimal difference in a raw logit doesn't really matter. Why does 0RL turn that tiny floating point difference into a fatal error?
Because of how we have to elicit reasoning in the first place. A base model does not know how to do chain of thought yet.
Right.
So to force it to try, the algorithm has to aggressively amplify low probability tokens. It essentially forces the model down weird, unexplored logical paths. Okay. And to do that mathematically, the algorithm uses something called an importance sampling ratio, which compares the probability of the new experimental behavior against the old base behavior.
And when you apply that ratio, you aren't just amplifying the rare reasoning token.
No.
You are simultaneously multiplying that tiny numerical discrepancy between the Megatron and SG-Lang logits.
Yeah, it creates a catastrophic feedback loop. Left unchecked, that tiny numerical gap compounds through the importance sampling ratio until the gradients explode.
And your entire training process just collapses.
Entirely.
So to summarize this absolute nightmare, you have a model that wants to endlessly ramble to farm rewards, and an infrastructure that numerically explodes if you try to force it to think.
Pretty much.
So to solve this padding issue and stabilize learning without relying on complex, handcrafted human rules, the researchers introduced a highly targeted 4-stage pipeline. Let's walk through how they overcome these hurdles.
Let's do it.
Stage 1 is first stage RL. How do they elicit reasoning without triggering that explosion?
Well, they start by attacking the engine mismatch directly in the math. They use a clipped importance ratio policy gradient, maintaining that token level loss to get the reasoning started.
Right.
But the critical modification is swapping out the numerator in the importance sampling ratio. Instead of relying on the inference engine's calculation, they compute the ratio using the actual training engine logits.
Oh, wow. So they force the math to reflect the true divergence of the training engine, basically neutralizing the gap at the source.
Furthermore, they bound this exploration with a KL divergence penalty. KL divergence measures how much the model's new behavior is drifting away from the original frozen reference model.
So keeping it grounded.
Yeah, because if you remove that KL penalty, entropy collapses. The model just spams gibberish and the reward crashes almost immediately.
So I guess think of the KL penalty like a tether on an astronaut. We want the AI to step out of the ship and explore new ways of reasoning out in the vacuum of space.
I like that analogy.
But if we cut that tether entirely, it drifts into complete randomness. It needs an anchor to its base knowledge. But wait, I'm confused. I had to push back on the logic here.
Oh, yeah.
If we are still aggressively amplifying low probability tokens in stage 1 to force the model to explore, aren't we still accelerating the engine mismatch? Like the tether keeps it close to the ship, but those micro errors are still multiplying inside the math, aren't they?
You've zeroed in on the fundamental limitation of stage 1, which is exactly why it cannot last forever. The gap absolutely still accumulates, just at a managed pace, and that is exactly why stage 2 is necessary. Stage 2 is self-distillation.
So this is a hard reset.
It functions entirely as a hard reset. Once the model has learned basic reasoning and generated a batch of high-quality chain of thought traces, they take the model and have it compress its own generated data using standard supervised fine-tuning.
Right.
Because this stage doesn't use the importance sampling ratio, it effectively zeroes out the training inference numerical gap that built up during stage 1. It clears the board.
It clears the board, and it also strips away the redundant verbose logic the model was using to game the system early on, right?
Yep, it does.
But the model still has that underlying behavioral issue. It still wants to be a lazy student and pad its word count. So how do they break that habit in stage 3?
In stage 3, or second stage RL, they fundamentally change how they grade the model. They shift from a token level loss to a sample level loss normalization.
Break down the difference between those two for us.
Sure. So under token level loss, the model gets a micro reward for every single valid step it writes, which encourages it to write, 1,000 steps.
Right.
But with sample level loss, the reward is normalized by the entire sequence length. Instead of getting paid per word, it gets a single fixed grade for the entire answer.
Regardless of whether it took 50 tokens or 5,000 tokens to arrive at the solution.
Exactly.
That makes total sense. If the prize money for solving the math problem is fixed at $10, you want to do the least amount of work possible to earn it. By shifting to a sample level loss, it entirely flattens the length inertia curve. The model can no longer farm rewards just by being verbose. It forces sustained improvement in actual reasoning capability.
Which prepares the model for the final stage, stage 4, third stage RL. This is where they introduce tier-based training.
Okay, what does that mean in practice?
They give the model adaptive depth by training it across a low 4K, medium 16K, and high 64K token budget. The model actually learns to adjust its reasoning effort based on how brutal the prompt is.
Oh, that's smart. So if it's a simple algebra question, it uses the 4K budget. If it's a terrifying quantum mechanics proof, it opens up the 64K window.
Precisely.
But let's rewind slightly, because pushing a 1 trillion parameter model to use 64,000 token windows brings us back to the infrastructure problem.
It really does.
Even with the stage 2 reset and the algorithm tweaks, the researchers knew the hardware and the numerical precisions themselves were still going to break at that sheer scale.
Yeah, the scale introduces physical bottlenecks that algorithms alone just cannot fix. Let's look at the mixed precision control they had to engineer.
Okay.
During the RL process, getting from raw logits to actual probabilities requires passing the numbers through a softmax function.
And a softmax function involves exponentiation, which in plain English means a microscopic rounding error in the base code doesn't just add up, it multiplies.
Right.
A tiny mathematical crack turns into a massive fault line instantly.
That is the danger. If you have a micro error in a logit due to engine differences, the exponential function blows it up into a massive gap in the probability ratio.
Wow.
It will spike the loss to infinity and completely tank your training run. So to fix this without slowing the cluster down to a crawl, the team used a targeted mixed precision strategy.
How did that work?
They kept the vast majority of the main model body in BF16 bfloat 16 precision, which is lower precision but much faster and cheaper to compute.
Okay.
But they computed the attention softmax and the language model head strictly in FP32, which is highly precise 32-bit floating point.
It's like building a massive skyscraper. You want to use standard steel, the BF16, for 99% of the framework to save money in compute.
Exactly.
But you use ultra-reinforced titanium, the FP32, strictly on the critical load-bearing joints where a microfracture would bring the entire building down.
Great analogy.
By isolating the high precisions strictly to those sensitive locations where the exponentiation happens, they eliminated the sudden spikes in the loss.
Yep, the titanium joint strategy kept the math stable, but they still had a massive latency bottleneck to solve. At 1 trillion parameters, handling 64K context windows requires context parallelism, or CP.
You have to distribute the sequence across multiple GPUs.
Right. But standard ring attention, where devices pass key value chunks sequentially in a circle, is simply too slow.
It's a bottleneck.
The latency is brutal because every device is waiting on a sequential chain.
So think of a classroom where 50 students have to solve a puzzle together, but they can only pass a single note to the person on their right, one at a time. It takes forever.
It takes way too long.
How do you untangle a sequential chain at a 1 trillion parameter scale?
You leverage the specific architecture of the model. The Ling model uses a hybrid architecture of MLA multi-head latent attention and lightning attention layers.
Okay, so they treat them differently.
Yeah. For the MLA layers, they used an all-to-all CP strategy. Instead of passing notes in a circle, all-to-all lets every GPU reshuffle the data along the head dimension using a single collective operation.
So the entire classroom just stands up and swaps their puzzle pieces simultaneously?
Yes. And it only works because MLA compresses the keys and values into a low-rank latent space, meaning the actual communication volume yelling across the room is tiny.
That's brilliant. And what about the lightning attention?
For the lightning attention layers, which depend on a small fixed-size state matrix due to their linear attention mechanism, they used a single all-gather operation to broadcast the states to every device instantly.
They bypass the sequential ring entirely.
Completely. It breaks the latency bottleneck while producing mathematically identical gradients.
So we have the minimalist pipeline. We have the sample level loss fixing the lazy student problem. We have the mixed precision titanium joints and the classroom broadcasting data simultaneously to unlock 64K windows.
The engine is finally stable.
So what actually happens when you let a 1 trillion parameter model run this pure RL pipeline with zero human data? Well, it teaches itself to think.
This is where we see the bitter lesson empirically validated. The researchers ran a control comparing this 1T model against a 104 billion parameter version, the Ling 2.5 FlashBase.
Running the exact same pipeline.
Yep. The 1T model didn't just learn faster, it hit a vastly higher accuracy ceiling. For example, it hit 84.2% on the AME 2026 math benchmark.
It's huge.
The 104B model simply couldn't come close to that ceiling, even with extended training. It proves that massive scale and representational capacity are prerequisites for self-evolved reasoning. The model needs a massive internal world model to navigate complex logic.
And the wild part isn't just the raw benchmark score, is how it got there. No human prompts told it to think step by step. No specialized reward heuristics told it how to format its answers. The researchers explicitly note that on their smaller 104B model, they actually had to handcraft rule-based rewards just to get it to format properly.
Right.
But at 1T, the model spontaneously developed elite cognitive behaviors entirely driven by trial and error.
It is remarkable. It started chunking its own thoughts.
It started adding step 1, step 2, and step 7, verify entirely on its own.
Spontaneously.
It developed parallel reasoning, where it would actively write alternative approach and explore multiple branches simultaneously before committing to a path. And my personal favorite, it developed anthropomorphism and context anxiety.
Yes.
It started generating phrases like, I might have a brain fart, or I will proceed to make an educated guess.
The context anxiety is a fascinating hallmark of reasoning. It is actively reflecting on the uncertainty within its own latent space.
It knows it might be wrong.
It recognizes when a logical path has a low probability of success and flags it.
But let me ask a structural question about this, because this debate is everywhere right now. Is the model actually planning ahead when it writes step 1? Or is it just greedily spitting out the next most likely token, and step 1 just happens to be a statistically probable string of characters in math textbooks?
That's a fair question.
It feels like we risk romanticizing a fancy autocomplete.
It is a vital distinction to make. But based on the analysis of the reasoning traces in this paper, the researchers view this as a form of localized forward planning, not just greedy token streaming.
How can they tell?
Because these traces capture an authentic, search-like trajectory, complete with trial and error, dead ends, and self-correction, the spontaneous emergence of these step markers suggests the model is setting a cognitive intent for the upcoming chunk of tokens before it generates them.
Oh, wow.
It has learned that chunking its computation this way radically optimizes its chance of securing the final reward. It is building a scaffold for its own computation.
It's setting an intent. That's incredible. But that leads us to the ultimate pragmatic question. It's amazing that the model builds a scaffold and learns to think like a stressed-out mathematician. But does this emergent chain of thought actually provide better utility for downstream ML tasks compared to human-curated data?
Right, the practical application.
If it takes 1 trillion parameters to generate this thinking, we need to know if it's economically useful to the rest of us.
To evaluate that, the researchers had to redefine how we measure chain of thought quality. Right now, the industry mostly just looks at final answer accuracy on a leaderboard.
True.
But if you want to use these reasoning traces in agentic workflows or to train smaller models, the trace itself is the product. So they evaluated the QKT across 3 dimensions independent of final accuracy: comprehensibility, reproducibility, and efficiency.
Let's focus on reproducibility first. Distillation. Because if you have a 1 trillion parameter model that can think perfectly, but you can't distill that knowledge down to a smaller, cheaper model, it is virtually useless for practical deployment.
Reproducibility measures exactly that. Whether a weaker student model can effectively learn the underlying logic. They took just 100K samples of this 1T model's reasoning and used it to fine-tune 2 smaller models, Quen 2.532b and Llama 3.370b.
Okay.
They then compared those results against models distilled from 800K samples of DeepSeek R1.
Wait, so they use 1/8 of the data volume compared to DeepSeek?
Yes, and the models distilled from the ring zero traces still consistently outperformed the DeepSeek R1 distilled models.
Wow.
They saw a 5.8-point gain on Quen and a 4.5-point gain on Llama. What this proves is that the spontaneous, step-segmented logic the 1T model developed is vastly more transferable.
Because it's a cleaner thought process.
Exactly. Because the logic is cleaner and less noisy, it encodes fundamental, generalizable problem-solving strategies rather than intuitive leaps that a smaller model simply doesn't have the capacity to follow.
And the third dimension was efficiency, which evaluated whether the generation gets to the point or rambles. They found that on mutually solved AM problems, the Ring Zero model averaged only 6,368 tokens to reach the correct answer.
Which is very lean.
Compare that to 14,000 to 17,000 tokens for other frontier models like GLM 5.1 or Kimi K2.6. There is a beautiful irony here.
Oh, totally.
By removing all human constraints, by getting rid of imitation learning and letting the model explore freely via zero RL, it actually taught itself to be significantly more efficient and concise than models that were explicitly trained to mimic human reasoning.
It is a profound irony. It turns out forcing an AI to mimic human step-by-step reasoning introduces all of our inherent verbosity and inefficiency.
Yeah, all our bad habits.
When you let a trillion parameters optimize purely for the mathematical truth under a sample-level loss, it strips away the human baggage. It finds a much more direct, computationally cost-effective path to the solution.
As we wrap up this deep dive into the Ring Zero paper, there is a very clear blueprint here for anyone building at the frontier.
If we connect this to the bigger picture, you don't need highly complex, over-engineered pipelines to scale RL to a trillion parameters. You need targeted stability.
Clipped importance sampling, a KL tether, sample level loss, and mixed precision titanium joints.
Exactly. If you provide that stable environment, the bitter lesson holds true. The model will autonomously discover cognitive strategies that vastly outperform our handcrafted rules.
Which brings me to a final provocative thought from the discussion section of the paper. It's something for you all to mull over as you head back to your IDEs.
Oh, this is a great point.
The researchers did a massive analysis on natural training data distribution. They noted that real-world data, even in advanced mathematics, has a massive long tail of easy problems.
Right.
Roughly 67% of the problems they analyzed could be solved in under 4K tokens.
Yeah.
But they found that overtraining on this natural frequency provides zero benefit.
None at all.
It simply wastes compute and completely stalls RL learning.
Mimicking the natural world offers no friction for the model at that stage.
So if an AI needs a dynamic curriculum of increasingly brutal difficulty to grow its reasoning boundaries, maybe the biggest bottleneck for the next major leap in AI isn't compute.
Then what is it?
Maybe it's that human data is just too easy. If a model needs to be pushed entirely out of its comfort zone to evolve, are we the ones holding the base models back?
Thanks for joining us on AI Paper Slop.